In this second part of Chapter 7, we're going to discuss the boundary conditions that we have to impose into our global system linear equation in order to determine the unknown nodal temperatures. For the first boundary condition, suppose there is a uniform temperature is specified at the left side of a plane wall as shown in this figure. To impose this boundary condition, we have to modify the global system linear equation as follows. Delete the first row and first column of the K matrix and modify the heat rate vector matrix as illustrated in the figure below. This is because, as discussed in the previous chapters, the first row and column correspond to the first unknown. For example, in this case, the first unknown is T1. The second row and second column correspond to T2 until the last row and column correspond to TL. And if the unknown is already specified, then that row and column is already not useful to be considered in the system linear equation. That's why we eliminate that row and column. Like in this case, T1 is already known. That's why we can eliminate the first row and the first column. Let's say if on the right wall is also specified, TL is equal to beta. In this case, we also need to eliminate the last row and the last column. And we have to modify on the right side by including the K1L beta, K2L beta until KLL beta. This is because whenever we eliminate the column and rows, we have to check the active row. For example, in this case, for row number 2, we check the column that we eliminate. For example, in this case, K21. If we multiply with the specified value, for example, T1, if it gives a constant value, then we have to bring to the right side. For example, in this case, this will be the constant value. Similarly, for the last row, K to L, if it multiply with the TL and give a constant value, then we have to bring it to the right side as shown here. The second boundary condition, suppose that convection occurs on the right side of a plane wall as shown in this figure. The effect of this convection can be incorporated by modifying the global system linear equation as follows. So we add H to the last element as shown in this figure. Second, we have to add H times T ambient on the last element in the heat rate vector matrix as shown in this figure down here. Now, let's say the convection occurs on the left side of a plane wall as shown in this figure. Similarly, this effect can be incorporated by modifying the global system linear equation. If the convection occurs on the right side, we modify the last element of K matrix and the heat rate vector. But if the convection occurs on the left side, this time we have to modify the first element of K matrix as well as the heat rate vector as shown in the figure below. Okay, now let's reconsider the composite wall problem in the previous video. This time, we would like to impose the conventional boundary conditions to solve the reduced system linear equation to determine the nodal temperatures, and then we would like to estimate the heat flux through the composite wall, and lastly, to estimate the heat loss on the right side of the wall. For the first task, we would like to impose the conventional boundary condition. In this problem, the convection process takes place on the right side. And remember, as we discussed previously, if the convection process occurs on the right side, then we have to modify the last element in the K matrix as well as in the R matrix. For that reason, in the K matrix, we need to add H value, which is in this case, its value is 1000. And in the R matrix, we need to add H times T ambient. And please take note that we have to use a consistent unit. Therefore, in this case, we have to convert the unit Celsius to Kelvin. Once we have done the modification to our global system linear equation, taking into account all the boundary conditions that may present in this problem. For example, in this case, there is only one boundary condition, which is the convection process that takes place on the right side. We can see the modification that has been done on the last element in the K matrix as shown here, as well as in the R matrix as shown here. Once we have done all the modification, then only we can solve our nodal temperature. By using the calculator, then we can solve the unknown temperature as shown here. Either you want to leave the answer in Kelvin or in Celsius, it doesn't matter. The third task is to estimate the heat flux through the composite wall by using the heat flux equation. This heat flux has to be calculated element by element. For the first heat flux, Q1 or QA, the K that we need to use is KA, L is LA, and the temperature that we have to use must be correspond to element 1, which is T1 and T2. And we get the answer, the heat flux for first element or for the QA is 37.5 kilowatt per meter square. While for element 2, Q2 or QB, the K that we need to use is the KB and LB, because it corresponds to element 2. And the temperature that we have to use must also correspond to element 2, which is T2 and T3. By calculate this value, we obtain the heat flux for the second element is 75 kilowatt per meter square. And the last task is to estimate the heat loss on the right side of the wall. By using this equation as shown in this slide, and T wall here is correspond to the wall on the right side, which is the T3. That's why we are using T3 in this equation. So by calculate this equation, we obtain the heat loss on the right side is 75 kilowatt per meter square. In this slide, we would like to discuss the last boundary condition in a steady-state heat conduction problem. Suppose that the heat flux is specified at the left side of a plane wall as shown in this figure. The effect of this specified heat flux is incorporated into the analysis by modifying the global system linear equation as shown here. We just need to add one more matrix to take into account the specified heat flux. The formula is negative Q naught if it takes place on the left side. If the heat flux takes place on the right side, then we have to modify the last term here, negative Q naught. Please take note that the heat flux is input as positive value if the heat flows out of the body, and as negative value if the heat is flowing into the body. For example, in this case, on the left side, the heat flux is flowing into. So when we want to insert into our matrix, then it will be negative Q naught. And consider the heat flux on the right side is flow out from the system. Therefore, in our matrix, the equation will be negative Q naught. This negative shown in this equation is a formula. Therefore, do not alter the negative sign in the formula. Now, let's reconsider the composite wall problem in the previous example. Suppose there is no internal heat generation in material A and no insulation on the left wall. Instead, a heat flux of 2000 watt per meter square occurs at the left side of the wall flowing into the body. Write the global system of linear equation for the plane wall and impose the specified heat flux on recognition and obtain the unknown nodal temperature. So in this case, there are some modification from the previous example. The first one, QA now has become 0. The K and the dimension of the wall is still remain the same. For wall B, no changes, and there is also the heat flux flowing into the body. So let's solve this problem. To solve this problem, first we have to check our K matrix. In this case, our KA, LA, KB and LB remain the same like in the previous example. Therefore, we can say that our K global matrix will be remain the same like in the previous example. However, for the heat rate vector, there will be some changes as QA now has become 0. Therefore, we have to compute again the heat rate vector for each element. For element 1, as now QA is equal to 0, therefore the heat rate vector for element 1 now has become 0. For element 2, it will remain the same like in the previous example, as QB is remain 0. Therefore, the global heat rate vector for this problem will be 0, as both elements having 0 values. Once we have the K matrix and the R matrix, then we can set up our system linear equation, which is K T equal to R. But we have to impose the boundary conditions at the first place before we can solve the nodal temperature. In this example, there are two boundary conditions. The first one is the convection process that takes place on the right side, like in the previous example, and a specified heat flux flowing into the body. For the convection process, similarly, like in the previous example, we have to modify the last element in the K matrix as well as in the R matrix. That's why we can see there is some modification have been done on the K matrix on the last element as well as for the R matrix. Similarly, like in the previous example. The new boundary condition in this case is the specified heat flux. Remember, for the specified heat flux, as it occurs on the left side, the formula will be negative Q naught, 0 and 0. So, in this case, Q naught is flowing into, as mentioned in the previous slide, when the heat flux flowing into, the value will be negative. That's why we replace the heat flux in this equation with negative 2000. And then we can solve this problem straight away by using the calculator and obtain the unknown nodal temperature as shown in this slide. Here I would like to show you the second example of steady-state heat conduction problem. A composite wall consists of 3 layers of materials as shown. The ambient temperature is 20 degrees Celsius. Convection heat transfer takes place on the left side of the wall, where the T ambient is equal to 800 Celsius and H is equal to 25 watt per meter square Celsius. Model the composite wall using 3 heat transfer elements and determine the temperature distribution in the wall, the heat flux, and the last one, the heat loss on the left side of the wall. The first step that we have to do is to draw the free body diagram of this wall. First, we have to define the nodes. As in this problem or in this wall, there are 4 layers. Therefore, we will create 4 nodes to represent each of the layer. Moreover, in this problem, the T4 for this wall on the right side is already specified with the value 20 degrees Celsius. Therefore, T4 is already known. And at the same time, the convection process takes place on the left side. So we can represent this convection process with this symbol that we put on the left side of our free body diagram. The next step is to determine the number of degrees of freedom. In this case, there are 3 degrees of freedom, which is T1, T2, and T3. The second step is to determine the element conductivity matrix for each element. So for element 1, which is correspond to the first material here, or the first wall, with K1 equal to 20 watt per meter Celsius, and the length is 0.3. By substitute these values, we obtain the K1 for the first wall or for first element. Second element, referring to this figure, K2 is equal to 30, L is equal to 0.15. Then we obtain the K matrix for element 2 as shown in this slide. And the last one, K3, by referring to this figure, K3 is equal to 50, L3 is equal to 0.15. And we obtain the K3 as shown in this figure. Once we have the element matrix for each element, then we can assemble it in the usual manner to obtain the global conductivity matrix for this problem, as shown in this slide. The next step is to obtain the element heat rate vector. However, since there is no internal heat generation in this problem, therefore, the heat rate vector for all elements are 0. And the global heat rate vector are also 0. And the next step, once we have obtained the K global and the R global, then we can write the global system linear equation, which is according to KT equal to R. Remember, at this point, the global system linear equation have no solution. We have to impose the boundary condition before we can solve it. After we have set up our system linear equation, the next step is to impose the boundary condition. In this problem, there are two types of boundary condition. The first one is the specified temperature that occur on the right wall, which is the T4 equal to 20 degrees Celsius, and the second boundary condition is the convection process that occur on the left side. Let's consider case by case. For the first one, the specified temperature, which is T4 is equal to 20 degrees Celsius, meaning that the unknown T4 is already known. So when it's already known, as mentioned previously, that row and column is no more useful to our system linear equation because its unknown is already known. Therefore, we can remove or we can eliminate row number 4 and column number 4 from our system. However, we have to check the row that's still active. For example, we start from the first row. The column that we eliminate, we have to check when we multiply with T4, it will give value or not. For example, for the first row, 0 times T4 will be 0, so nothing changed. The second row, 0 multiplied with T4, also 0, nothing changed. But for the third row, we have a value here. So this value, when it's multiplied with T4, it will generate a constant value. So that constant value, we have to bring to the right side. Okay, for those who really not understand, I will show you by taking out this row number 3 and write it down as in equation. So in row number 3, we have negative 200 T2 plus 500 T3.33 multiply T3 minus 3.33 T4. T4 is 20 equal to 0. In system linear equation, whenever we have a constant value, normally we have to bring to other side. So when we bring to other side, the value will be positive. That's what we're trying to do. Okay, that's what we're trying to do in this solution. So on the right side, there will be some modification. So we will have this term coming from this value. So when we bring to the right side, that's happened to this value. And the second boundary condition is the convention that takes place on the left side. Remember, when the convention takes place on the left side, we have to modify the first element in the K matrix. So in the K matrix, we need to add H in the first element. And on the right side, or in the R matrix, we need to add H times T ambience. Okay, so when we solve this problem, we will obtain our final system linear equation. Then we just need to use our calculator in order to determine or to solve the unknown nodal temperature as shown in this slide. The next task is to determine the heat flux of the middle wall. So we are consider only this middle wall, meaning that it corresponds to T2 and T3. In order to calculate the heat flux, we just need to use the heat flux equation and we just need to substitute with the correct values. As we are talking about the heat flux of the middle wall, then we have to use the K2 and L2 in our equation. And for the temperature, as mentioned, it corresponds to T2 and T3. So by replacing all those values into the heat flux equation, this is K2, this is L2, this is T2 and T3, and we obtain the heat flux for the middle wall as shown in this slide. The last task is to determine the heat loss on the left side of the wall. So the equation for the heat loss is given by this equation, which is Q equal to H times T wall minus T ambient. Since we want to calculate the heat loss on the left side of the wall, so the T wall in this case will be our T1. So in this case, T wall will be T1, T ambient is given from the question, which is 800. H also is given in the question, which is 25. So by substitute those values into this equation, and we can obtain the heat loss on the left side of the wall. So the negative value here means that the heat is being consumed.